In the next 20 minutes, I'd like to give you a brief introduction to quantum computing. And the story of quantum computing addresses the collision or intersection of two fields in science. The first is the area of computer science that explores the use of man-made machines to solve mathematical problems. And the second is the field of quantum science or quantum mechanics. This is an area of science that lays down the foundations, the laws of physics that governs our universe down to the tiny, tiniest scales. Now, for many decades, these two fields of science had nothing to do with one another until in 1985, we got to realize that there is actually a very deep connection between these two fields, and that basically gave birth to the field of quantum computing today that I'll be talking about. Now, today's computers might be considered as perhaps humanity's greatest achievements, or at least one of humanity's greatest achievements. It's really phenomenal pieces of equipment that can do really amazing things. And therefore, I think you'd be surprised to know that the same concept of computing machines that we have today, these fascinating instruments, are actually the same machine that Alan Turing in 1936 thought of when he hypothesized how would he construct a computing machine. Now, some of you might know Alan Turing from the movie The Imitation Game, a movie that aired about a year ago, exploring Alan Turing's work during Second World War as he basically deciphered or broke the Enigma, the Nazi encryption machine. What Alan Turing had in mind when he just hypothesized, theorized about a computing instrument, he didn't build one, was a very, very primitive piece of instrument. And the concept was, let's imagine we have a very long piece of tape, and we can write on that tape, we can have zeros and one on it. We have a head, a magnetic head or a read-write head that can erase a bit there, zero, and turn it into one. It can move right and left. And it does this based on instructions that are given to it, and the instruction that you see on the head right now is number 4. So for the instruction number 4, this computer here would see I have a 0, so my instruction is to replace the 0 to a 1, move to the right, and change my head instruction to number 5. This sounds like a very, very primitive computing instrument, but it turns out that this very basic concept is what's called the Turing machine, and everything computable can be calculated using that machine. Now, the bigger surprise possibly is that that machine, known as a Turing machine, is in fact nearly identical to the computers that we have today. And so you can ask yourself, well, what is the difference then between our computers today that look really fascinating and that primitive machine? And in fact, the only difference is, to some extent, the number of operations that this machine can do per second. In the early days, 1947, where the first transistor was basically built inside a chip, a semiconducting chip, the number of operations we could do is on the order of 10 or 100 per second. And over the course of 50 or 70 years, our computers have developed tremendously, and today we're able to basically run maybe 10 to the 9 operations per second. But the fundamental concept of computing is exactly the same, or nearly exactly the same, as the Turing machine. A breakthrough in this stagnation occurred in 1985 by the physicist of David Deutsch, who made a very peculiar statement. And that statement is, the ultimate limits of computation is set by the laws of physics. And as we know, the laws of physics are governed by quantum mechanics. And so the question is really, what is the link between computation and quantum mechanics? So to get you into the right mindset about quantum mechanics, I'd like to ask you a little riddle. And the riddle is, what is the difference between a classical mechanic, the one that fixes your car, and a quantum mechanic? Anybody have an idea? Guess, it's okay. Yeah. So a quantum mechanic can fix 2 cars at once. This is an excellent answer. My answer actually would have been that a quantum mechanic could both drive and fix his car at the same time. And I know this sounds counterintuitive, and it's okay. This is what happens with quantum mechanics. It's very counterintuitive, but I'd like you to get into this mindset where things that defy your intuition are not necessarily wrong, and just flow along. And hopefully, you'll get a sense of why quantum mechanics helps with computation. So here's a zoom in on an atom, an artist's rendering of an atom. We have a nucleus that attracts electrons, and these electrons are surrounding the atom. And in fact, a more precise rendering of an atom is what I'm showing here, where I have the nucleus, and the electron is depicted as a cloud rather than a particle, which basically tries to emphasize that it's living around this nucleus all at once, all around. Okay? Now, to highlight this element, I'm going to introduce two nuclei and one electron. And in what you see up there, the electron is mostly surrounding the left nuclei. And this means that if I were to measure where is this electron amongst the two nuclei, I'm always going to find it on the left. And that's why I've written the letter L on the left. I can also prepare these pair of nuclei and one electron where the electron is on the right. And if I were to measure where that electron is, I'm always going to find it on the right. It's deterministic. And that's why I've labeled it right. But just like the riddle that I gave you, we can also prepare these two nuclei and one electron in a way where the electron cloud is actually surrounding both nuclei. And to exaggerate things, we can actually separate these two nuclei such that we have one electron who's actually equally hovering around the two nuclei separated in space. And if we were to ask now, where is that electron, we would get two possibilities. On occasion, we will find it on the left, and on occasion, we will find it on the right. But there is nothing deterministic that can predict the outcome of that experiment. This is fundamentally unknown, and therefore I've written the letters left and R on the side because these are the possible outcomes of the experiment. Now, to give you a sense of something that could be at two places or do two things at the same time, I'd like you to think of waves. Waves are objects that are not local. You see that you have a wave and it's present at multiple places at the same time, and that is the essence of how we can understand features, certain features of quantum mechanics. We know that waves have peculiar or particular manifestations. For example, in one of the experiments downstairs that you can go and explore, there is a laser light that is shined on two slits. And what we know is that when you shine waves onto two slits, because of the non-local nature of the wave can pass both on the right slit and on the left slit. And what that does is give an interference pattern on the screen. You're not getting the shadow of the two slits on the screen. You're getting something more complex. And that more complex pattern indicates that we have waves in the system. So now let's just ask what would happen if we replace this laser with an electron gun. And we're going to shoot electrons, particles, one at a time through the double slits. And when we do this experiment, what we find is that on the screen we get spots. For each electron we send, we get a spot. But you see the spots are messy and it looks noisy. But if we collect enough of these electrons, eventually what we find is a pattern that looks exactly the same as the pattern of the waves that we got when we did the experiment with wave or light waves. And what this suggests is that the electrons are actually passing through the slits both on the left and on the right, like our quantum mechanic, at the same time, and giving rise to an interesting pattern on the screen. And note, we could not predict for any individual experiment where we would find the electron, but the probabilities, which are the intensities of these spots, is something that we can predict. And we see that we have high intensity stripes and we have low intensity stripes at some other locations. So let's take this now one step further and consider two sets of pairs of nuclei and one electron, one on the top and one on the bottom. And I've prepared them in a way that on the top the electron is on the left and on the bottom the electron is on the left. And if I ask what are the measurement outcomes, where would I find my electron? It's going to be left and left because that's how I prepared it. I can do the same thing and prepare the two electrons on the right and ask what is the measurement outcome, and deterministically I'm always going to find it on the right. But now let's introduce this superposition and prepare the upper system in this left and right and the bottom system in the left and right and see what are the measurement outcomes. And so the measurement outcomes are multiple. I could find electron on the left in the upper system and on the left in the bottom system. I can find it left and right, and I can find right and left. and I can find right and right. So I have multiple possible outcomes that can come when I perform the experiment. But perhaps the most important thing to note is that in this particular example, there are no correlations between the measurement outcome on the top and on the bottom. Note, for example, that for the outcomes left on the top, I can get both left and right on the bottom. And the same thing, if I have right on the bottom, I can get both left and right on the top. They're uncorrelated. They seemingly look entirely random. But one thing that quantum mechanics allows us is to prepare a system in a way that has only a subset of the possible outcomes, okay? And here I'm showing an example where I've prepared the system where there are only two possible outcomes, left and right and right. And I want to emphasize why this is extremely creepy. Let's imagine I send one pair of these nuclei, an electron, up to the moon and keep the other one here with you. And I measure the one on the moon, and I find left. Since this system was prepared in this peculiar way that the only measurement outcome possible when the upper is left is that the other system is also left, you see that even though I'm on the moon, you're going to measure left, and there's no way around it. And if I were to measure right on the moon, you're going to measure right on Earth, and it's going to happen instantaneously. So there is something very peculiar about what's happening here. And this is something that if you blow up to the classical or macroscopic scale would seem very, very unintuitive. It's basically like describing a coin toss experiments or two coin toss experiments where if I measured left or heads on one, the other one would automatically fall on the head. And if I were to measure tail, then deterministically, the other one would fall tail, and yet to begin with, I couldn't predict what my measurement outcome would be at all. It could be either head or tail with equal probability. This feature of quantum mechanics is different from superposition. It's called entanglement. And entanglement is a key element and something that bothered Albert Einstein tremendously. He struggled with this concept for many, many years, and he gave it this kind of name, spooky action at a distance, because he really couldn't, didn't like it. And he actually spent many of his late days trying to show why this kind of concept is not correct, and he failed. Today we know that this description of superposition and entanglement is consistent with every single observation we have about our universe, and so we have no indications of any violations of these concepts altogether. So what's the connection with computing? So here's a classical bit. When the system was deterministic, the electron is always on the left. Let's call that 0. And when the electron is on the right, let's call that 1. That's our classical bit. But here, the quantum bit is the possibility of not only having this bit being in 0 or 1, but also being in the superposition of 0 and 1 at the same time, our quantum mechanic. So let's take it a little bit further. Suppose I had 4 bits. I want to build a computer, so this is a small computer with only 4 bits. And these are classical bits for now, and I've prepared them in the state 0. All the electrons are on the left. If I were to do a computation, I would have to operate on these bits, and one operation would be a bit flip. And the bit flip will just change the location of the 2 nuclei. And you see that we've switched bit number 2 from 0 to 1. That's how a classical computer works. It operates on the bits by flipping them depending on various inputs that it has. Let's look at this now from the quantum world. So now we've prepared these quantum bits. They could be in these superpositions of 0s and 1 at the same time. And moreover, we have prepared in a way that we can have multiple measurement outcomes. And you see here an example of all the bits simultaneously 0, together with a situation where all the bits are at the same time 1, and another instance where there is 0, 1, 0, 1. In fact, there are 2 to the 4 possible configurations of these bits. And whereas the classical computer at any given instance is at one of these possible configurations at any given time, you see that our quantum computer is at many of these configurations at the same time. In fact, it can be in up to a number as large as 2 to the n configurations at the same time. This is really large when n, the number of bits, gets to be very large. When we do a bit flip operation on this computer, note what happens. We're flipping the sides again of the 2 bits. So all the realizations, the possible measurement outcomes, switch zeros to ones and ones to zero. So one single operation changes the states of many possible outcomes at once. You get a sense of parallelicity. There is a very strong power embedded in this kind of quantum computer. So if I want to compare these quantum computers based on quantum bits and classical computers, we argue that our classical computers are basically Turing machines. They're no different from what Alan Turing envisioned many, many years ago. Whereas quantum computers that use entanglement and superposition, in fact, are more powerful than Turing machines. This is, in fact, the first time in the history of computer science that we have been able to conceive a computing machine that is more powerful than a Turing machine. So the question is, okay, so we have a more powerful computing machine. What can we do with it? How would it impact our lives? So here's an example. It's a mathematical example of a problem that quantum computers can solve much, much better and faster than a classical computer. And the problem is finding the prime numbers that construct a large number. So here's a number, 15. And I'd like to ask you, what are the prime numbers that make it up? Yeah. 3 and 5. That's correct. So when we discuss the difficulty of a problem, we always make the problem bigger and bigger. So this was a 2-digit number. Let's go to a 3-digit number. So here we have the number 143. 13 times 11. Boy, we have a quantum computer here. 13 times 11, that's absolutely correct. Let's go one step further. Let's add one more digit, 4,633. Note, the computing time gets longer and longer. That's the essence of a hard problem, that as the problem gets bigger, the computing time gets bigger exponentially, much faster than the size of the problem is growing. 41 times 113. What about a number that has 100 digits? I can tell you that a classical computer would require a few months to figure that out, okay? So why is that interesting? Why is factoring prime numbers a problem that we would be interested at all? In fact, you're all interested in that because you're using it every day many, many times. It is the underlying concept of encryption. When you send out a message or an email, your phone encrypts your message, and it uses a hard problem that is very hard to solve, so that any classical computer that would try to decipher your code will take months or years to figure out what that code was, okay? I want to emphasize that if we were to try and give this task to a quantum computer, for the same amount of time, we would only require 1,000 quantum bits, would be equivalent to 1 billion classical bits for the same problem. So this is the power of a quantum computer. So what else can we solve with quantum computers? In fact, we know a few problems, quite a few, that quantum computers will aid us in solving very effectively. One we talked about is the encryption. The other one is searching or data mining, searching in big databases. It turns out that quantum computers we know today can do that more efficiently, more effectively than a classical computer. We can also, of course, use quantum computers to simulate how nature behaves on the microscopic scale, where it is just governed by quantum mechanics. There are, however, a very large list of problems that we don't know yet whether quantum computers will be able to solve more efficiently than the classical one. The field is still in its infancy, and so we hope we will discover many, many more problems that classical computers are weaker than quantum ones, but the answer is not known for many of those. So where do we stand right now with the question of classical computers and quantum computers? So to give you a sense, the pathway or trajectory that classical computers have undergone is really tremendous. We've started in the 1958 with the first integrated circuit. We had only 4 elements, 4 bits on that piece of semiconductor in the chip. And in 1970, we already had 1,000 bits. And to give you a sense of the process that classical computers went through, I show a picture here of this hall here. And let's imagine that people are bits. We can probably fit into this space here 1,000 people. And it will feel okay, maybe a little bit crowded, but okay. And that's 1970. By the year 1980, we would be able to fit into this space the entire visitors to a stadium, 100,000 people. So that's a little bit more crowded. 1995, we can fit here the entire population of Tokyo, 10 million bits. And 2010, not even today, we can fit in the entire population of China into this room. So the process is really phenomenal, but what we need to understand is that this process cannot continue forever. As we're shrinking things more and more to put more and more things into a small space, the size of each bit is getting smaller and smaller, and we expect that in the next 10 or 20 years, the extrapolation, the same development would require that our bit size would be the size of individual atoms. We won't be able to squeeze them further. So this miniaturization process is bound to reach an end, and we're seeing it slow down already in the past several years. In contrast, the trajectory of quantum computers is really just beginning. In 2000, we had 1 quantum bit, and today we roughly have 10. We are on a solid trajectory, but it is going to take a couple of more decades to get to a scale where we have really a large number of computers. So my message is, stay tuned. This is a really fascinating field that is developing today, but don't start saving to buy your next quantum computer. Buy your classical one first. It's going to take us a little bit of time. Thank you.